Day 7. So yesterday we set for ourselves the geometry, and we also now have a good understanding of what our computational domain should look like. Now let's actually get into the open form part of it, where we'll talk about how do we make this entire computational domain happen. The way in which we do it, as you can see here, we'll do blockMesh, then surface feature extract, and ultimately snappyHexMesh. Let's take a look at individual of these steps. How do they work?
So the strategy here becomes essentially to define what our computational domain would look like. We do that by using three different files here. There's the blockMesh text, there's the surface feature extract text, and there's the snappyHexMesh text. Currently I have a test case present here with me. So in here, as we can see, there's the blockMesh text, there is the snappyHexMesh text, and there is the surface feature extract text. Now individually, each of these files need to be configured so that our wrench geometry can be meshed appropriately. Let's take a look at the blockMesh dictionary file. So as we can see here, we have a bunch of things happening. We first of all have the keyword scale. So OpenFOAM works on meters for its length. So scale essentially scales it down. The 0.001 essentially scales down to millimeters. The vertices that we see here, these describe the extremities of our particular bounding box here in the X, Y, and Z coordinates. Now, based on these vertices that we have, we are essentially generating these blocks here, a hex block with these vertices with 40 and 40 divisions in the first and second directions and 120 in the third direction. The first direction being the X direction, second being Y, and third being the Z. And we've also defined the boundaries here with the inlet, outlet, and walls. Notice that the walls are set to the type symmetry, essentially going through the slip boundary condition as opposed to the no slip boundary condition. So for me to show you what this mesh would essentially look like, let's just run the blockMesh command. So we see that we have the block cell size of 0.01. and we have a number of cells, 192,000. Let's take a look at what this mesh would look like. So as you can see, we have this particular box here. The box has uniform cell size across all three dimensions. Seemingly 10 mm mesh is what we've made here. Now, ideally speaking, we should have the wrench placed somewhere around inside. Let's take a look at what that would look like. So there is the wrench, as you can see here. The wrench is essentially situated in the middle, and from the inlet it is at a certain distance, from the outlet it is at a certain distance. We are trying to analyze what would happen if flow occurs from the inlet right here, and what that would or how it would impact the drag over a particular wrench here. So the first thing we need to do is help identify where the wrench is in our computational domain. So let's do that by using the snappyHexMesh and the surface feature extract. Coming to the snappyHexMesh dictionary file, we essentially configure it with a lot of base level, default values, but the main areas where we sort of divert is primarily this here. With the features, we've given a level 4, and the refinement surface we've given level 4 as well. Resolve feature angle set to 30, and a location in mesh which is strictly inside the fluid domain. Nothing really changes in snapping, and the only thing we've done here is added 5 layers to our particular wrench with a final thickness of 0.4 with relative sizing set to turn true. We've also ensured, since our wrench has a very sharp angle near the jaw, and it also has very sharp angles near to the handle, we've essentially added the feature angle and the slip feature angle to 360. So there's that. Let's take a look at the surface feature extract dictionary file. So with surface feature extract dictionary, there's not much to discuss here. Only thing it will do is it will take the wrench STL file, it will extract the edges, which will be, determined by this included angle as to which edges to extract. And once they are extracted, the refinement for the feature edge refinement that we did right here will essentially be applied on top of that. So this helps in primarily capturing the feature edges much well, because Snappy has tendency to miss out on sharp edges, primarily due to how cancellation translates into snapping. So this step ensures that this edge refinement is done really well. So as we can see, the meshing is done. We have been able to create close to 5 layers here with 97.1% coverage, so to speak. Let's take a look at what this mesh looks like. So I've taken a cut plane for our particular wrench body here, and you can see. So this is the first stage here with cancellation. Then we have snapping here. Now let's do the layering. Great. So we can see that the layers that we require have actually been made near to the wall. We do have pretty good coverage here. So now that our mesh has been made, let's move forward. Tomorrow we'll discuss how exactly does the case setup look like, and we'll talk about the intricacies of why a certain model was chosen, and then just run a preliminary analysis. So see you tomorrow.